but let's get started. This is just enough assembly for Compiler Explorer. Come on in, just getting started. My name is Schau Knatten. I am from Norway, and I work in a company called Zivid, where we make these cool robot eyes on the top here. If my pointer worked, there we go. Yeah, so these are 3D cameras that serves as eyes for robots. And we mostly do C++. We do a few other languages as well, but C++ is what I mainly concern myself with. And if any of this sounds interesting to you, then feel free to have a chat at the conference or on Twitter later or something. I also run this website called cppquiz.org, which is a C++ quiz site, which you might enjoy. And I hang out on Twitter a bunch on these various accounts, so yeah, say hi on Twitter if you like. But we're here today to talk about Compiler Explorer. And who has used Compiler Explorer? Yeah, most people. And who tends to understand all of the assembly outputs that it shows you? Yeah, not me at least. So that's why I made this talk. Compiler Explorer is a really nice website where you can paste your C or C++ or whatever on one side of the site, and then on the other side it shows you the assembly code that the compiler made for you. And why is that interesting? Come on in. Why do you want to look at assembly code in 2022? And that's because you write your C or C++ or other higher-level languages. You write that code for humans to read, right? And then the compiler has to turn that into some machine code stuff that runs on the CPU. So if you want to know what the compiler did to your code, then looking at that machine code is what you have to do. And then for each machine instruction, there's a corresponding assembly instruction. So assembly is just a nice way to read the stuff that the compiler did to your code. Yeah, and then you can put in different compilers, different compiler options, and try, like, how does that affect stuff. So if we have a look at the site here, we can see that, don't worry about the code. This is just some random code I typed in here. So we can see here to the left that we have a bunch of C or C++ that I just pasted in here. And I selected GCC 12.2 here. I can select MSVC or Clang or like different architectures and stuff. And here I can put in some compiler options if I want. And then I get to see all the assembly code that the compiler generated. And it's also a bit nice that I can, like, if I hover over some of the assembly stuff, you can see to the left that it highlights, oh, this is where these instructions came from. And the other way around, if I highlight this line, okay, this caused these instructions. Then I can hover over here, I can get some tool tips, and it's quite convenient stuff. And this is not a lot of code, but there's quite a lot of stuff going on over here with all these D-word putters and pushing and moving, and it's quite a lot of stuff over here. And then my promise to you is that in 50 minutes, we will understand all of that code, not only what it does, but also why it's there. And that's not going to be because I'm going to go super fast. I'm actually going to go pretty slowly from the very beginning. All right, back to the slides. Yeah, please ask questions during the talk. So when the code is up here, we're looking at it, you have any questions, try to ask during the talk. You can just shout out and I'll just repeat the question. Because it's better to explain stuff while you're wondering about it and while we're looking at it and have the context. But if you have more like, I would also like to know about this other thing type of questions, then please hold those to the end. And today, most of the slides are going to be this slideware toy emulator kind of thing. So we're emulating a x86-64 CPU. So we're always going to see the CPU in the middle of the screen. And the CPU has a bunch of registers. So anytime you want to do something with any data, really, you have to get it into those registers. And for each example, I'm then going to visualize the registers that I use in this particular example. So for the first example, I'm going to use RDI and RSI, which are just two arbitrary general-purpose registers that we can use for stuff. And for each example, I'm just setting the register to 0 in the beginning. That's just for convenience for the slides. That doesn't happen in real life. So here we can see RDI and RSI all containing zeros. And these are 64-bit registers. The talk is about x86 64, so I'm displaying those in hex over here. OK, let's get some assembly code up. So here is a complete assembly program. And assembly is not necessarily easy, but it's a very simple language. It's just like one instruction, one line. And you start with instruction name, and then every instruction has 0 or more operands. So for instance, this first instruction is called move, and it has 2 operands, RDI and 2. And just like in C++, in assembly, move doesn't mean move. In assembly, it happens to mean copy. So move RDI2 means to copy something. And there are different syntaxes for assembly, and the most popular one and the default one on Compiler Explorer is the Intel syntax. And in the Intel syntax, you kind of have to read backwards. So move RDI2 means to move the literal 2 into the register RDI, and not move the register RDI into 2, whatever that would mean. So let's, and I've also put up this little debugger indicator thing, this little orange line here next to the next instruction that I'm going to execute, so we can like step through like this and see what happens. So if we then do execute this first line, move RDI2, we then just moved the value 2 into RDI here. Then we can do the same thing for move RSI4. Let's put the value 4 into RSI. And then we can add these 2 registers. So I'm going to say add RDI, RSI. I'll add the 2 values in these registers together and get 2 plus 4 equals 6. And then we are used to, in our higher level languages, to say int result equals a plus b. But there are only 2 operands here. So in assembly, you don't get to specify where to put the result. It will just put it in the first operand. So add RDI, RSI is more similar to RDI plus equals RSI. So if I add 2 and 4, I get 6, and I execute this instruction, and it puts the value here in RDI, because that was the first operand to add. OK, that's our first full assembly program. Any questions so far? OK, that was registers, but we are going to need some memory as well, right? You can't just use these registers and make a full program. You need to have some data in memory. So I put up some memory here, and I'm going to, in all the examples, I'm just going to be using the stack. And on the stack, you can push stuff, you can pop stuff, but you can also address the stack, and you put things at this place, and this memory address. And everything I say about memory addressing for the stack is also going to be valid for the heap and for global data and whatever. So it's just easier to just use the stack. On x86, the stack is growing downwards. So we can see here on the top, we have the address to the left. So this will, of course, be a 64-bit address on x86 64, but I'm just truncating it a bit. So at address B3, we have the byte 0. At address B2, we have the byte 0. At B1, we have the byte 0, and so on. And the stack then will have come from above, and it's growing downwards like this. There's also another register in this example called RSP, and that's the stack pointer. So that's pointing to the current top of the stack. So whenever you push or pop something, the current top of the stack is where we're going to push and pop to and from. So we have RSP over here. And I also put up this RSP indicator over here, so you can see that, well, the RSP has now B0. That's the top of the stack. So I'm pointing to it over here as well. Right, so then we can do our next example, which is just about pushing and popping some values onto the stack. So first, I want to put a bunch of bytes into a register. So I do move again, which copies value from somewhere to somewhere. I'm going to copy this rather long value into RDI, just so that each byte has a different value, so it's easier to see what goes where on the stack. And then we get to push RDI. And notice that we're not saying how much to push or where to push or anything. We just say push this register. And that's because it's a 64-bit register. We know that we're going to have to push 8 bytes. Where do we push it? Well, the stack pointer is over here. So we know that we're going to then occupy these 8 bytes here. And the only question then really is what is going to end up over here at AF? What's the value of this byte after I execute the next line? So there's one right answer, and then there's the plausible but wrong answer, and all the other ones are implausible, I would say. So it has to be either FE or 10, and as it turns out, it's FE. That's because x86 is a little endian architecture, so the least significant byte goes on the lower address, and the most significant byte goes on the higher address, and that's why you get FE over here on the stack. Right, then we can also pop from the stack, and again, I just say pop and where to pop. So now it's going to see, well, RSP is down there at A8, so I'll pop from there. I'm going to pop 8 bytes, because it's a 64-bit register, so I'll pop 8 bytes from here, and the stack pointer is moved up again. So I don't have to move around the stack pointer manually. That happens automatically when I push and pop. But pushing and popping only takes you so far. We also want to be able to address memory. So we want to say, at this address, I want something to happen. So let's do that. Let's first get some bytes into some registers. Get all of these 3s into RSI, all of these 2s into RDI. And now we have the move instruction again, which we've seen many times. It's copying something. It has 2 operands. The last operand is RSI. That's where I'm going to copy from. And the first operand is where I'm going to copy into. And I'm going to copy into keyword putter RSP -8, whatever that means. Keyword stands for quad word. So a byte, that's 8 bits. Then you have words, which are 16 bits. Double words are 32. And quad words are 64 bits. So quad word putter means this is a pointer to a 64-bit value. So we know that it's a 64-bit value, and we're talking about it's like a pointer. This is an address that we're talking about here. And then inside of the square brackets, I can put any kind of tiny little arithmetic expression to compute the address that I'm interested in. And let's say I want to put this value at the top of the stack. I'm not going to use push. I'm going to manually set it to that place in memory. So I will then do RSP -8. So then this expression is going to do RSP -8. Well, that would be A8. And I will copy RSI into memory at that address. So if I do that, you can see we got all these 3s into memory. And we also see that the stack pointer didn't move because I didn't push on the stack. So the stack pointer is just where it was. I just wrote some bytes somewhere in memory. Yeah, and this is actually how a local variable looks like. If you have like long foo as a local variable in your function in C or C++, this is exactly how that looks like. So we have our value here in memory, and this assembly line here is also something you typically see when you have a local variable. Memory addressing can also be used in other instructions. In addition to move, you can use it, for instance, in add. So if I do add RDI, and then this keyword putter RSP -8 thing again, I'm going to read the value from RSP -8. And the keyword putter is kind of dereferencing that, so we get the value rather than the address. And then we add it to RDI. So we take all of these 3s from over here, add them to all of these 2s in RDI, and we get a bunch of 5s. And as we saw before, add stores the result in the first operand, so we get a bunch of 5s in RDI. Yep, then we can read and write local variables. And before we continue, I want to mention register sizes. So originally, when the 8086 processor came out, like the first processor in the x86 architecture, that was a 16-bit processor. So then we had 16-bit registers called AX, BX, CX, DX, and so on. But we also had these other names, AH and AL, which just refers to the 2 halves of AX. So they have the high part and the low part of AX. But if you write here, it's actually just one register called AX, but these are just names for putting a byte in the lower or higher part of the AX register. And then the 386 came along with a 32-bit architecture. We got the EAX register. It's still only the EAX registers. All the others are just like aliases for parts of it. And then x86-64 came with 64-bit registers. And now we only have the RAX, but you can use the names for the smaller parts of it. And then, quick quiz question, how big is an int? It depends, yeah. If you read the standard, it has to be at least as big as a short, but it doesn't really say. But typically, if you're on x86-64, if you're on Linux and Windows, and yeah, it's typically 32 bits. So here are some typical sizes that you'll see in these registers. You can put signed or unsigned longs in the 64-bit ones, signed or unsigned int in the 32-bit, short in the 16-bit, and then signed, unsigned, or just plain chars in these 8-bit ones. So, if ints are 32 bits, let's redo the previous example just with 32 bits, because ints is like probably my favorite data type. I use it all the time, so let's see how ints look. So then things are a bit different. I'm using ESI and EDI in the code here, but I'm still visualizing the full register. So if I copy this int here into ESI, you can see I only wrote the lower half of RSI. And then I can put some 2s into EDI. And now I can do the same thing again, take the register and just write it somewhere in memory. And this time it reads a little bit different. It says D-word for double word, because quad word is 64 bits, double word is 32 bits. So D-word putter is a pointer to a 32-bit value. And I'm also doing RSP -4. On the previous example, I did -8 because I needed 8 bytes for the 64 bits. I just need 4 bytes for these 32 bits. So if I run this, it copies the 3s from ESI into memory here. And again, I can add whatever is at RSP -4, all of these 3s we just wrote, add it to whatever is in EDI, all of these 2s, and again, store the result in the first operand, so EDI then becomes all of the 3s plus all of the 2s are all of the 5s. And then we can read and write ints. But reading and writing like single ints and longs and stuff, that's not really enough. We need some arrays as well. And arrays also happen to be a good motivation to talk about some other things that are coming up shortly, so let's do arrays next. Let's just start with putting some values into memory. This time I'm using word putter for 16-bit values, just to, for variation and to save some space. So we put all of these 1s, 2s, 3s, and 4s at these addresses here. So stack pointer, -8, -6, -4, -2. So I'll just run all of those through. And then we can see that over here we have all of these bytes that we just wrote. And these are just 8 bytes in memory somewhere. So these don't have types. Assembly doesn't have types. The CPU certainly doesn't have types. These are just bytes, right? These could be 8 individual bytes. They could be like part of a MAC address or an employee record or what have you. But for our example, we push them as 4 16-bit values. So logically, we are going to treat them as an array of 4 shorts. But these could be any bytes, really. And now I happen to be interested in getting the 4th element of this array. So I want to get this value here. And the way I do that is to, first, before I want to get that, I want to have a pointer to the array. Because the way we deal with arrays in C and C++ is basically you have a pointer to the first element. Every time you try to do something with an array, it just turns into a pointer to the first element straight away, right? So we want to have a pointer to the beginning of the array. And to do that, I need to store the address somewhere. So again, the first element is at RSP -8. So we've seen the square bracket before. That's how you compute an address. So we take RSP -8. So that's B0 -8 equals A8. That's the address I want. But this time, I don't want to read the data there. I don't do the move, dword putter, whatever thing. I want to just keep the address. I don't want to dereference it. And the way I do that is with the instruction called load effective address. So LEA, load effective address. It's only going to compute that little expression I have here and then store that into RDI. So I'm not dereferencing the value, I'm just taking the address. So if I execute that, I now did RSP minus 8, and I put that into RDI. So you can see RDI is now pointing to the beginning of my array. And then I have a pointer to my array. And now I can get to the thing I started talking about a bit too early, which is I really want to look at the fourth element of my array. And how do I do that? I have a pointer to the beginning, and then I want the fourth element. So I have to skip past 3 elements, so I have to add 3 times the size of the element. So I need to add 6, right? I have a pointer to the beginning. I have to add 6 to that address to get to the fourth 2-byte long value. So I do that. I do the move thing again, RDI plus 6. That's the pointer to the address, plus 6 bytes to get to the fourth element up here. And I move that into AX, because AX happens to be where I want to have my result for this example. So that's how you can get to memory, but this is just like a regular memory access thing that we saw before. And it's not really useful to be able to have to hard code the offset every time, right? When you want to index into an array, you typically want to have an index. So I have a pointer to the beginning of the array in RDI. Let's say I want to have the index in RSI. So I'll put 0 into RSI. So now my index is 0. I want to get at the first element of the array. And what I can do then is I can take my pointer to the beginning, which is in RDI, and then I just add the index times the size of the element. And the size of the element is 2. So I'll do RDI plus 0 times 2. So I just get RDI. So this expression here then gets me the first element which lives here. And if I execute it, I got these ones over here into this register. But now I have parameterized the index. I no longer have this hard-coded plus 6 thing. So I can just do increment RSI, just RSI plus my index thing. And now RSI is 1. And then I can do exactly the same expression, right? This is identical to the 1 2 lines above. I can just do base pointer plus index times the size of the element. And now I get, if I execute that, I get the 2's into RAX. So now I have parameterized this little line of assembly code to be able to take an index and a base. And this sounds like something you could use in a loop or a conditional, so that's what we're going to get to next. I should have picked a glass instead of a bottle. Right, conditionals. Let's start with an if. We want to implement an if that compares 2 numbers, and if the first number is greater than the second number, we want to store true. Okay. Very interesting program, but let's just get some values into some registers. We put 3 into RDI, 2 into RSI, and now we want to check, is RDI bigger than RSI? And we don't have if or switch or any of that like super modern stuff in assembly. But what we do have is we have compare and we have goto. And since goto is considered great, we can do everything we need here. So the first thing we do is to compare. We do compare CMP, compare RDI to RSI. And if we execute that, nothing really happens. So what compare does, it compares these numbers. But we didn't even tell it, like, compare what? Like, which comparison are you interested in? Is it less, equal, or like, what do you mean compare? So what compare does, it just compares these numbers in all the ways at the same time and stores away some states in some flags that we can later check. So on the next line, we do check. So we did the comparison, and then we have jump greater, JG. So jump if greater is going to then check these flags and say, well, if the comparison told us that the first operand was larger, then we jump. If not, we don't jump. And RDI was indeed larger than RSI. So we do actually jump down to this label over here called .greater, which is just a label that we made up. And when we jump down here, we can then write 1 into RAX, because that's going to indicate true, that the first number was indeed larger. Yeah, so there we got 1 into RAX. If we do exactly the same example, but we do 2 and 3 instead of 3 and 2. So this time we put 2 into RDI and 3 into RSI instead of the other way around. Then we compare RDI and RSI. So this time RDI has 2, RSI has 3, and we compare those, and nothing happens because compare just sets some flags in the flags register. And then again, we do jump if greater. This time, the first operand was not larger than the second, so we don't jump. And when you don't jump, what happens then? There are no blocks to jump to. Like, you just don't jump, you just fall through to the next line. So when we just fall through to the next line, well, then we know the condition was false, and then we store false in RAX to indicate, no, it was not bigger. And then there's one very important thing that we still have to do, and that's, first to store the false. Now we have to jump, unconditionally jump to the end of the if thing, because if we don't jump here, we've just stored false. If we don't unconditionally jump, we'll just fall through down here, and we're going to also store true, and that's wrong, right? So we just jump down to the label at the end of the if thing. So this, when you're used to C and C++ and stuff, it's kind of the other way around, because we have kind of the else block is kind of up here, and the if block is kind of down here. So it's sort of in the other way around than what we're used to. So that's something you will often see. There are a bunch of ways to compare numbers, or there's just one compare, and then there's a bunch of things you can do later. So compare, what it actually does is just subtract the second operand from the first. So if I do CMP up1, up2, it just does up1 minus up2, except if you did the actual sub-instruction, it would actually store the result then into up1. But that's not what you want. It just subtracts this one from that one and doesn't store the result anywhere. And when an expression like that is executed, these flags get set. So if up2 is larger than up1, that means the result of the subtraction is negative, so then the sign bit gets set. If they're the same, if you subtract the number from itself, you get 0, and then the 0 bit gets set. So there's just a bunch of bits like this that get set, and then you can do all these conditional jumps later to see, inspect these flags. So jump equal, well, I will just check then if the 0 bit got set. So that's how jump equal and jump not equal are implemented. And yeah, similar for, then you have jump less, less or equal, jump if greater or equal. But yeah.
Something like add or subtraction also set the flags?
I'm not sure what happens with add. Oh, yes, repeat the question. Thank you. Someone was asking, if you just do add or subtract, do you also set these flags? If you subtract, I think the flags get set. If the add gets, there might be some flags. I'm not sure.
Overflow.
Yes, overflow. Yeah, that's a good point. If you add, you could overflow. So we've talked about comparison and jump less equal. So you tell it like which comparison were you interested in. But it's just comparing some 64-bit values. Like, what do these mean? Like, the same 64-bit pattern could mean like a very large unsigned number or a negative signed number. So signedness, like how you interpret these bytes, is really important for whether one is larger than the other. So all of these jump less and greater, these are for signed integers. And then if you want to compare it as if they were unsigned, you have to use some other instructions. And then less and equal, those names were taken, so then we have below and above for unsigned. So if you want to do unsigned comparisons, you do jump below, below or equal, above or equal. Yes, okay, ifs are done. Next up, loops. And loops are very, very similar to ifs, actually. Because we don't have if and switch, of course, we don't have for, do, while, any of that good stuff. So we're going to have to use our comparisons and conditional jumps again. And now I want to implement this little C program here. What the program does is it's a for loop where I iterate from 1 to 3, non-inclusive, and I just increment with 1 every time. And I've conveniently named my variables the same as my registers, just to make it easier to correlate. And for each time around in my for loop, I'll just add the counter thing, RCX to RAX. So I'll just accumulate all of these RCX in RAX. Pretty simple for loop, and let's see how we implement that in assembly. I first set my counter variable, RCX, to 1, and I set my accumulator, my RAX, to 0. And then I have a .for. That's just a label for the beginning of my for loop. And the first thing I do when I do a for loop, I want to check my condition. Do I actually want to start iterating even on the first round? So I compare RCX to 3. And then the flags get set, nothing else we can observe. And then we do jump equal. So if RCX was indeed 3, if we've arrived at 3, we have to jump out of the entire for thing so that we're done. But RCX is just 1, so we don't jump, we just fall through to the next instruction. And then we can do the RAX plus equals RCX thing and just add RCX to RAX. So 1 plus 0 equals 1, and we get 1 in RAX. Then we get to the plus plus RCX, so we just increment RCX. And then we can jump back up to the beginning of the for loop. Are we 3 yet? We're not, so we just fall through. We don't jump. Keep adding RCX to RAX. Increment RCX to bump our counter. Jump back to the beginning of the for loop. Are we 3 yet? Yes. This time, RCX equals 3, so we're not supposed to go into the loop body. So instead, we do jump equal. Yes, we were equal. We jump to the end for label. And then we have loops as well. Yes, time for a real example on Compiler Explorer. So I guess I should zoom this a bit. So we have this fancy math function here called sum. It's going to take 2 ints, a and b, sum them together, and return the result. Very, very exciting code. And then, as I said before, I happen to be using GCC 12.2. And this is what GCC 12.2 generated for me for this code.
Hey, could you try to switch to an I team? I think it would display better on the projection.
To switch, how do I do that? Yeah, the question was, can I switch to a light theme?
I think it's more, say the other or more.
Over here?
Yeah.
Settings. Oh, coloring, site theme, light. Har du sett på maken? Yeah, nice. So at the end of the presentation, I'm going to ask for some tips for Compiler Explorer, but this is the best tip I've gotten so far. Right, so this is the code that GCC generated, and we can just copy that back into our slides. So now this is assembly code that GCC wrote. This is not my code, this is GCC's code, and it decided to use quite a bit of registers, so I had to put some more registers here. So we have RDI, RSI, RAX, RDX, RSP, and RBP. Yeah. Push RBP. That's the first instruction in our sum function. So we're about to start executing our function. But before we can start executing, we have to figure out how to get the arguments. We had the A and the B. Someone will have called us with some values as arguments that we need to get to. And how do we do that? And that's up to the calling convention. So every system has a calling convention, which tells you, among other things, how to get stuff into and out from functions. And on Linux, where I wrote this talk, we have the systemv AMD64 calling convention. Microsoft has one that's very similar. And it says, well, if you're going to pass a few integers to a function, just leave them in these very specific registers. Because that's a really fast way to do it. So whoever called us here, they apparently wanted to add 2 and 3. So they will have, before calling the function, they will have put 2 into RDI, which is the first integer register, and 3 into RSI, which is the second integer argument register. So before we are even called, these values will have been put into registers. They're already available, so we can just read them out from there. The next thing, or the first thing we then do when we start executing our function is to push RBP. And that's again due to the calling convention, because the calling convention tells us, well, whoever was calling you, they might have been using these registers for something, right? So you have to not destroy whatever was in these registers. And it doesn't apply to all registers, but RBP is one of the ones you're not allowed to overwrite. So the first thing we do is just to push RBP onto the stack, so that the last thing we do can be just pop it off again, right? So whatever value was in RBP when the caller called us, well, when we return back, that value is still going to be there. So if I execute that, I will then push RBP onto the stack, and I don't really know what the caller had in its RBP, so I didn't put any values here, but I've now pushed it onto the stack, and we can see that the stack pointer has bumped since I pushed something on the stack. The next thing we do is to copy RSP, which is the stack pointer, into RBP. So we kind of make a backup of the stack pointer in RBP. And we're not going to need it for this example, but the reason we do that is when we are executing this function, we could be pushing and popping and doing all sorts of stuff that makes the stack pointer jump all over the place. And if we want to do all of this relative addressing that we've seen before, like RBP -4 and whatnot, it's nice to have this stable pointer to the beginning of our stack frame. So we take the stack pointer, make a copy in RBP, and the B is for the base pointer. So we have like a base pointer to the base of our stack frame. So then no matter how much we do with the stack pointer, we always have this stable pointer to the beginning of our stack frame. Okay, then let's see how GCC wanted to implement this stuff. Well, it got these values in these two registers, so it's just a matter of adding those registers together. But it's doing a few more things. It's moving EDI, which is the first argument A, and ESI, which is the second argument B, to our sum function. It copies those into memory at RBP -4 and -8. So I'll run these two, and then we can see that our value 2 is here, and our value 3 is here. And that kind of seems a bit pointless, but these are parameters. So these are L values, right? So you have to be able to dereference these and take their address and all that L value stuff. So better put them in memory so that we can actually do that. So now these are actual variables in memory that you can take the address of. You can look at them in your debugger and all of that stuff. Next thing GCC decided to do is to then copy them back into some registers again. I don't know why. It just decided to, well, let's take them from memory back into some other registers. So now finally we have our 2 and our 3 here in RAX and RDX. And finally, we're going to sum them together. So add EAX, EDX. We'll then just 3 plus 2 equals 5. And then we said we had to restore the base pointer because whoever called us, they were probably using the base pointer for something. So we better pop it off the stack. And then we return. And how do you return? Like we have this value 5. We need to return it somehow. And again, the calling convention tells us how to do it. And the calling convention says, if you just want to return a simple integer or a pointer or something simple like that, just stick it in RAX or EAX for a 32-bit value. And then the caller can just read that register to get the value. But this add thing here, it already put the result in EAX. So we don't really need to do anything. The return value is already in the correct register, and we can just return. And then ret just returns instruction to wherever it was before the function was called. And that's a quite cumbersome way of adding two ints. So
what would happen if we compile with optimization? Would it still
yeah,
like
that's my. He's asking exactly what I was going to say, and that's what happens if you do some optimization here. It's a very good question. And this looks a lot nicer. right? No memory access, which is super slow. Not all of these instructions moving stuff back and forth. So this is nicer. It has just one single instruction to add stuff, and then we return. But LEA, remember that one? Load effective address. So why are we loading addresses? We just want to add 2 ints that we got in some registers. We don't need any addresses. Well, LEA is what it does in the square brackets. It's just maths, right? You can just like do some simple plus and minus stuff in here. So, well, you can, and the thing is, it's just everything is just bytes, right? So LEA doesn't know if these are pointers or if there are data or whatever. So LEA can just actually sum stuff together, and it has this nice property that you are allowed to tell it where to put the result. So we get our 2 parameters in RDI and RSI that we add together, but if we had added those, the result would be in RDI, and then we'd have to move it into EAX. But LEA, well, it can just do everything in one operation, and it doesn't care that this isn't an address, really. It just does the maths and is happy. So that's a very, and it's fast as well. So yeah, this is a very simple way to do the sum function. And then I'll just go back to the slides, just so we have the URL correctly. And now we have seen variables, seen memory access, arrays, control flow with if and for, and started looking a bit at functions. So when we have all of this, we can then finally get to the holy grail of programming paradigms, which is, of course, procedural programming. So let's do that. Then I have to change the theme here again. Maybe I can refresh. Super fast. Nice. And then there's a preview that doesn't go away. All right. OK. So here's a slightly more advanced example, very similar to the previous one. So we used to have sum. In the previous example, we took sum of a plus b. This time, we just make it a bit more advanced. Now we're getting into like really hardcore math here. We're going to take a and b, sum them together, and then times 2. So we're going to double the result. So it takes a and b, the sum times 2, takes a and b, adds them together, and then calls the times 2 function. And the times 2 function just returns the whatever argument times 2. And then you see to the right, this is the assembly code that GCC happened to make for us. And then again, we can bring all of that into our little emulator thing here. And now I'm going to use a bit more stack. So you remember the stack was growing downwards like this. And then I simply just look at that drawing nicely. Yeah, so the stack just wraps around. It grows downwards like this, and then it continues from up here and keeps growing down like this, just to have space on the slides. OK, so we are in the sum times 2 function. It took 2 parameters, a and b, and the first thing it wants to do is to add those together before passing it to the times 2 function. So it's very similar to the previous one. It pushes RBP so that we don't destroy RBP for our callers. We can pop it, restore it later. Next thing we do is to take a copy of the stack pointer into RBP. So it just copies RSP into RBP. So now both RBP and RSP are pointing to the top of the stack. And this time, that's nice, because we are going to start messing around with the stack pointer. We are going to subtract 16 from the stack pointer. So now it's nice that we have this stable pointer to the beginning of our stack frame, because then we can do all our address computations relative to that. And then we have kind of like limits for our stack frame. So RBP, this is where our stack frame starts. RSP is where it ends. So when you call another function, that one can start using the stack from the stack pointer here. Yes, and then again, whoever called us, they were again very interested in what happens with 2 and 3. So they put those 2 values into RDI and RSI, the first 2 int registers. And then I'll just skim through this. GCC decided to do exactly like before, copy those two values into memory over here, and then copy them back into these registers. So we have the 2 and the 3 over here, just as exactly as in the previous example. And now we want to add these together and then pass that to the times 2 function. So adding is just like before, add EAX, EDX. It's going to add those two together. So it takes 2 plus 3 equals 5 and store it in the first operand, EAX. And then we have 5 over here. And now it's our time to call another function. So far we've only been called. Now we are calling someone, and we have to fulfill the caller's responsibility in the calling convention. So we're going to take this value 5 and call times 2 with it. And then we need to put it into EDI. Just like whoever called us put their value 2 into EDI, now we have to put our 5 into EDI. So we take the result from 2 plus 3 that we have here, put it into EDI like this, and then we can call the times 2 function. So when we call that, then control then moves down here. So we have an instruction pointer, which I'm not including in these examples, but it's kind of like the orange indicator here. The instruction pointer is now pointing down here instead. And the times 2 function does the usual preamble, push RBP so we can restore it later, take a backup of the stack pointer in RBP. Then it has gotten this value in EDI, and we want to have a proper L value that we can take the address of and everything, so we better put it into memory. And so let's put it back again into a register, just like we've seen many times now. And now we come to the times 2 function is supposed to multiply its parameter by 2. And GCC, even on O0, figured out, well, mul is kind of slow, so, or probably that's why it did it. So let's do add instead. Just add the thing to itself to multiply it by 2. So we add 5 plus 5, that's A. So now we have A in RAX over here, and then we have to return it. So we have to get it into EAX, but it's already there, so we don't have to copy it anywhere. We can just pop RBP. So now we can see that that was nice, because now we get our RBP back when we get back to our function. And return. And then return just transfers control back up to where it came from. So it just returns to the next instruction after the call instruction. Then we see one new instruction here that we haven't seen before, but it's just a combination of two things. So we have this leave instruction. All it does is just like a shorthand to undo these two things. So it will first use RBP to restore RSP, and then it's going to pop RBP to restore those. So I'll have like 2 clicks to do that one. The first thing it does is it copies RBP into RSP, so it resets RSP to point down here where it was pointing. And then we pop RBP off the stack, and then RSP jumps up again, and then RSP and RBP have both been restored for whoever called us. And now we're in the sum times 2 function, which did A plus B, pass that into the times 2 function. So now we have to take the return value from that function and make it the return value of our function, because we want to return that result to whoever called us. But, well, we just called a function, and we know that the result from that function is going to be in EAX, and that's exactly where we need to put it to return from our function, so we don't really need to do anything. We can just call ret to return to the caller. And again, do you have a question about optimization?
I would think that no question, but I think it would collapse quite a bit here as well.
Yes, it's going to collapse a bit is the comment, and that is correct. So if we first look at the times 2 function, it takes int I, returns I times 2. So it's doing the LEA trick again. It then just adds the number to itself, puts it into EAX, so it doesn't have to first add it and then move it into EAX. It uses the LEA instruction, and then just returns. For the sum times 2 function, we get these two ints in EDI and ESI. So we first have to add those together. So it adds ESI to EDI, so EDI now holds the sum of them both. And then you can see it just inlines the entire times 2 function. So there's no function call down here, it just inlines it. And it can do that because it's in the same compilation unit, so that's why it's able to inline everything. So now this collapses down to a very nice short function.
One thing I think
Yes, yeah. So RDI, that's the name of the full yeah, okay. I can. The question was just what's the difference between EDI and RDI? RDI is the full register, so that's the actual thing on the CPU, if there's even like an actual thing on the CPU anymore. But anyway, EDI is the name for the 32-bit part of it. So yeah, so it's kind of, it's like these are the names you'd expect. You get these into EDI and ESI, which are the lower parts of RDI and RSI. And then LEA, we're kind of abusing LEA here. We're tricking it into doing some maths for us. And LEA only knows about addresses, and all the addresses are 64-bit. So LEA expects to get 64-bit register, so we just we just give it the full register. And then the top part is just going to be zeros. And apparently we're then allowed to just write the lower half into EAX. So yeah, that's that example. And then we can go back to our initial example, and I'll use Olafur's hack here. Fantastic stuff. Remember I showed you this code in the beginning with like, I'll just zoom out a bit, with all of this assembly stuff, and I told you that in 50 minutes you would understand what all of it does and why it's there, and I think we have achieved that. So let's first look at this computer function. So we have this computer function here. This is just random code, so don't care too much about the implementation. And I'm going to go a bit quickly through it because we don't need to like deeply understand stuff. I just want to like show you that you have already seen all of these things. So the computer function takes an int a and an unsigned int b, and then it has a for loop that just like counts down this b value until it's as long as it's larger than 0, and just adds all of those to a, and then we just return a. So then we can look at the implementation in assembly here. We can see, I think I didn't mention it, but it annotates also like at the top here. This is the stuff that came from the computer function. So we push RBP so we don't destroy it for our caller. We take a copy of the stack pointer into the base pointer so we have something stable to address relative to. Then we have gotten our two ints in these two integer registers, and we push those into memory somewhere so that they are actual L values, real variables. And then we get to the for loop. So the first thing we do is to jump down to L2, JMP, unconditional jump. Okay, let's jump down here. And yeah, here we got A into RBP minus 4 and B into RBP minus 8. So minus 4, that's A, minus 8 is B. So when we're down here, we're going to see, are we going to jump into the for loop or not? So we compare B, which lives at RBP minus 8. D word putter is the double word pointer thing we talked about earlier, compared to 0. If we are 0, if we're not 0, jump if not equal, then we jump here into the loop body. And this comparison thing might as well have been up here. It doesn't really matter. It's just how it happened to end up. Then we do the thing we saw before. We take these two variables from memory, A and B, put it into these two registers, add the registers together. Result goes here. So now we have the result of this A plus equals B here. That result is now in EAX. And then we need to move that back into memory, because A actually lives here in memory at RBP minus 4. So we take the result of the addition and then update the real A in memory. And then we do sub to subtract 1 from B. So this is the B in memory. We subtract 1 from that. And we're back at the comparison. So are we 0? And whenever we get down to 0, we don't jump if equal. And then we just fall through to the next instruction. And then we just have to return A. Well, A is here at RBP minus 4, so we put it into EAX, the return register. We pop the base pointer and return. Okay, so we've seen all of that before. We know why it's there. And then we have this caller function. And this caller function is going to call the compute function. So we're going to call the computer function with the two literals 1 and 3. And we call that I. And if I is less than 10, we just return it. If it's bigger than 10, we just return 10. We don't want to deal with these huge numbers like 11 and 12. So yeah, let's see if we can understand the caller as well. So we push RBP. Yeah, this one we see before. We subtract 16 from RSP to set aside some stack for place on the stack for our stack frame. Then we're going to call a function with 2 literals. So we put those into the first 2 arguments that the calling convention says to use. And we call the function. We get the result from the computer function in the return value register, EAX. We put it into memory. So this is now where our int I lives. That lives at -4 from the base pointer. And then we have to check, is it less than 10? So let's compare it to 9, apparently, and jump if greater. Right? So instead of jump if it's less than 10, we just jump if it's greater than 9. So if it's greater, then we want to, then it's a really big number that we don't want to deal with, so we just jump down here. We put 10 into our return register. If it's not greater, we just fall through. Then we take the value of I here at this place in memory, put it into the return value register. And then we have to remember to do this unconditional jump. So we jump over the other branch, and we can leave and return to restore RBP and RSP. And this is not interesting code in any way, and it's not very advanced, but it's hopefully enough fundamentals to how things work that it's a lot easier when you use this stuff and you Google things, then you probably have more of a, fundamentals to understand what Stack Overflow tells you. And a few tips. You can hover over here, as I said before. You can like control or right-click and jump to some assembly documentation, which helps. Then you can Google stuff, of course. It helps to make a local reproduction that's as simple as possible. So your IDE probably can help you to inline some stuff, or you can copy and paste and delete things until you have a standalone reproduction. Compiler Explorer also has libraries. So if you want to use Boost or FMTlib or Eigen or whatnot, then you can just add those, and you have them available in Compiler Explorer. Sometimes it helps to use ints instead of complicated types, unless you're interested in what happens to your actual type, and that can be nice. And don't try it on your full project, right? This is not like, how does my program work? It's like, what's the answer to this specific thing I wonder about? So I think Matt Goldbolt, who made Compiler Explorer, initially did it to figure out the new range-based for loop when that came. Does it perform as well as the normal for loop? And then he just looked at the assembly code and said, well, the assembly code is exactly identical, so then I don't need to measure performance on all my targets and stuff. I know it's going to be the same. So we can do that, or like, is this template going to inline well, or yeah, things like that. Yeah, we have a couple of minutes left, so oops. Any other tips from the audience, except from the Light team for presentations? One thing, you can execute the code. I didn't show that, but you can like tick the box to execute the code, which is really useful. And you can side-by-side compilers, so you can like compare GCC to Clang to MSVC or whatnot. That's pretty useful as well. So I have a shortcut in my browser to open Compiler Explorer with GCC, Clang, and MSVC next to each other, which are the compilers I care about for my project. Yeah, then I think that's it. 1 minute left for questions, if there's anything. Yeah, question, you'll get a microphone here.
Better. So it looked like you have to kind of remember which variable goes in which place in the memory. So is there a way to kind of replace that or show that in the assembly code? So like an address table maybe, or do you know?
Well, you have the thing where you can it doesn't work that well for parameters, but maybe the int I thing here. I'll scroll down a bit. Oh, that's too much. Slowly back up. There we go. Maybe you can see. Yeah, I'm not aware of any like fundamental techniques to like visualize it for you, but at least on Compiler Explorer, when you highlight this line here, you can kind of see here that this line is highlighted, RVP -4. But I think that's the best I can give you.
Okay, thanks.
And yeah, hopefully you don't have to write too much assembly yourself. Any other questions? Okay, then thank you for coming so late and listening to me talk about assembly. Thanks.